Okay, so hi everybody. I am Vanderlei. I'm a professor at University of Maryland, Baltimore County, UMBC, and I'll talk about the HARP CubeSat satellite, which is the hyperangular rainbow polarimeter CubeSat. So here you have a picture of my team, or the names of my team, involving all the way from students to postdocs and engineers. And HARP is a 3U CubeSat. The bus was built by Space Dynamics Lab in Utah, and the sensor, the polarimeter, that's our technology demonstration, was built at UMBC, and was built as a demonstration of multi-angle or hyperangular polarization measurements, multispectral polarization measurements from space. So HARP is basically a wide field of view lens. It's 110 degrees along track and 94 degrees cross track. Depending on the orbit altitude, it would give you global coverage, and that's what we're demonstrating. And in the back end of the optics, we have a prism that splits the image into three geometrically identical images, except that these images are polarized at 0, 45, and 90 degrees, so that we can derive the I, Q, and U Stokes parameters. So there are several technologies that we're demonstrating here. So HARP is funded by the ESTF2020 program as a technology demonstration. And there are several aspects of technology that we're demonstrating here, including this hyperangular spec filter that goes into the focal plane, so that allows us to select the different viewing angles and the different wavelengths. So HARP was launched in November 2nd last year. Was deployed from the ISS on February 19th, and we got our first line image on April 15th. So I'll show you some of the results that we got so far. So HARP also has a innovative sampling scheme. So that's how we do the sampling with HARP. So what you see here on the left-hand side, so that's a original raw image on HARP, and you see the lines here that are the stripes. So as the spacecraft is moving, we select several push brooms, and each push broom, like this one, would be the forward viewing angle. There's one at nadir, that would be the nadir viewing angle, or the backward viewing angle. And each push broom corresponds to a different wavelength and or different viewing angle on the ground. And here on the right-hand side, you have an example of a push broom RGB image that was done with, our RGB wavelengths for a given scene, for a given region. So here's an example of our end-to-end data processing system. So we start from the image, from the video that you saw in the previous slide, and here is now a projection on the ground. So what you see here is HARP. So you see the contour here of the HARP image, and that's projected on the top of a GOES image, GOES ABI image. I said projected on top, so they are actually completely independently geolocated images. So what you see here is the result of our geolocation from HARP compared with a GOES ABI image. So we are very happy with our end-to-end data processing system. So HARP was technology demonstration not only for the electronics, the optics, the filters, but also for our whole data processing stream from end to end. And here you see a false color image showing the same thing, HARP over ABI. So this was our first full image. So this is over Lake Titicaca in Bolivia and Peru. And here is the salt flat, that both targets that we are planning to use for calibration. So these are the images that we got so far. So one of the big challenges with our CubeSats is the amount of data. So we do collect a huge amount of data if we run with all angles, all wavelengths, and relatively high resolution. So communication is one of our biggest challenges. The payload has been working perfectly. We had not a single issue so far with the payload, but communication has been a big challenge in terms of getting us a large amount of data, although it has been improving. So those are the full images that we have so far. So we have 9 scenes around the globe, and we are picking targets depending on some science objectives. So HARP objective is to look at clouds and aerosols, and here, for instance, you have an example on June 13th of a dust plume coming out of the coast of Africa. So this is right before that huge dust plume that's coming out of the coast of Africa and traveling all the way to the U.S. So this is right before that event, a dust plume coming from the same region. Our objective is really look at aerosols in general and cloud properties. So HARP has the ability to measure cloud and aerosol microphysical properties. This is an example of that scene that you're talking about. So the scene over the coast of Africa with the dust plume. So this is a HARP RGB image over there. And here is a video with the 670 nanometer wavelength. So HARP has 4 wavelengths from 440 nanometers to 870 nanometers. And here you see a multi-angle image of that and give an idea of the type of information that you're looking for. So you see how the intensity of the image will change as a function of angle. You see here over land, here over water. There are changes over the dust plume that's hard to see in this animation, but that's what we are after. So those changes as a function of the viewing angle that will allow us to do the retrieval. So here you see 60 different viewing angles. So HARP is up to 60 different views of the ground at 670 nanometer. And up to 20 viewing angles for the other 3 wavelengths. This is an example for hyperangular sampling, so the 670 nanometer that I was talking about. So this is again over Lake Titicaca that we are using for calibration. We also have the Uni Salt Flat that we also use for calibration of the system. And here you can see that for a given pixel on the ground, you can observe that pixel from all the different viewing angles. And for instance, in this particular case, I'm plotting the reflectance as a function of scattering angle. And you see the whole sun glint profile over that piece over the lake. So that's what you allow us to do a retrieval. So we can fit this profile that has the atmospheric component and the surface component. We can fit our models and perform our retrievals. This is an example of a retrieval of cloud properties. I'm just showing the result of 1 pixel here as an example. So this is a cloud deck over the ocean. And you can see here when I plot the polarized reflectance as a function of scattering angle, I can fit now what we call the cloud bow profile. It's basically a rainbow produced by cloud droplets. And you can see that by fitting that cloud bow profile, we can retrieve with very high accuracy the effective radius of the droplets of the clouds. And more than that, we can retrieve the effective variance of the droplets. So basically the width of the droplet distribution. So those are 2 pieces of information from the cloud microphysics that are very important in terms of interpreting the cloud properties and the ability of the cloud to precipitate. This is really the first demonstration ever from space of a hyperangular cloud bow retrieval. So this is the first time it's done from space, and you have the whole profile for like a single pixel or a small group of pixels. And we can do that for the whole scene. So if you take a whole cloud scene, you can, for every pixel of the scene, do the retrieval of the effective radius and the effective variance. This case in particular is a demonstration from our aircraft versions. We call it HARP, but we expect to do the same for HARP CubeSat and do the cloud bow retrieval for every pixel of a cloud scene. And we can do that for heterogeneous clouds and for homogeneous clouds. That's on the cloud retrieval. On the aerosol retrieval, you see here an example also from our HARP, where we are looking at a smoke plume, and we do the retrieval of optical thickness and the other microphysical properties. So this is an example now of the aerosol retrieval with HARP CubeSat. So this is very preliminary because we are still using our pre-launch calibration. This calibration has been done now over 6 months ago. So we're still working on doing post-calibration with it in space. But nevertheless, you see here an example of 2 pixels. We only took 2 pixels here over water, and I'm showing you the fit of the models over the hyperangular profile that we have at 4 wavelengths, the 4 wavelengths. And from that, we can do the aerosol retrieval. So this is an example of aerosol optical thickness you see here. We expect to be able to do the whole microphysical characterization, measuring size, single scattering albedo, and the refractive index. We have done with the aircraft, and now we'll do with HARP CubeSat. And I'll just end here by showing you the HARP polarimeter family. We have HARP CubeSat, we have HARP that I showed you data from both of them. We're currently working on HARP2 for PACE, for the PACE satellite. This will give us global coverage in 2 days and it's supposed to launch in 2022. We're also working on other concepts for these hyperangular polarimeters with higher resolution and extended wavelength range from UV all the way to shortwave infrared. Thank you.